So in the previous lecture, we were discussing about how to express a vector as a linear combination of standard bases of Rn. Standard bases are basically standard bases of Rn. What are standard bases? It is basically a set E1, E2, so on, En. E1, E2 are basically the standard bases of Rn. Where what is E1? E1 is a vector having components of this kind, 1, 0, 0, so on, 0. E2 is a vector 0, 1, 0, so on, 0, and so on. En is a vector having all the elements of this kind in the last one as well. If we write standard basis of R cube, then how can we write it? It is basically E1, and E1 is nothing but 1, 0, 0. E2 is 0, 1, 0, and E3 is 0, 0, 1. These are called standard bases of Euclidean spaces. R2, R3, so on, R4, and so on, Rn. Any element in Rn can be written as a linear combination of its standard bases. How do we write it? For example, if we have any x belongs to Rn, x is a vector in Rn. For simplicity, let's suppose that x belongs to R cube, and we can generalize it. If x belongs to R cube, then x can be written as how? It has 3 components, x1, x2, x3, or x, y, z. Any question? Didn't we already do this? Yes, let me repeat it so that I have to use it in linear transformation, how to define the standard matrix. So this thing can be written as x1, 1, 0, 0, plus x2, 0, 1, 0, and plus x3, 0, 0, 1. Okay. Now, it can be written as x1, e1, plus x2, e2, plus x3, e3. Okay. So x can be written as a linear combination of the standard unit vectors, where x1, x2, x3 are real numbers, and e1, e2, e3 are the vectors. So x, what is this? Is a linear combination of standard unit vectors. Standard unit vectors R cube. So any x which belongs to R cube can be written as a linear combination of its standard unit. How can we derive standard matrix of any linear transformation? For example, last time we talked about the linear transformation. I hope you know what is a linear transformation and how to define it. For example, if we have any linear transformation T from Rn to Rn, and it is defined by T of x is equal to A times x, where x belongs to Rn, which is the element of the domain set Rn. How to define this? How to find this matrix? How to find A, where A is called standard matrix of T, matrix of the linear transformation T is given here. How to find this? Now we know that this x can be written as a linear combination of standard unit vectors so on, plus xn e n vector. Where e1, e2, so on en are the standard unit vectors of Rn. Now, after writing this, we can apply the transformations on both sides. That linear transformation, T. If you apply T on both sides, T of x is equal to T of x1 e1 plus x2 e2 plus so on plus xn en. Okay. We apply that transformation on both sides. Now, as T is a linear transformation, so what? How can we write this? If this is linear transformation, can we expand this T? Anyone? How can we write it? Do you know the property of the linear transformation we discussed last time? There was a property which I told you, the principle of superposition. What was that? T of alpha 1 x1 plus alpha 2 x2. How can we write it? Anyone? It's a property of linear transformation. How do we prove a given transformation to be a linear? There are two properties. The two properties were T of x1 plus x2 is equal to what? Anyone? Can you tell me?
Sir,
G.
sir, T of x1 plus T of x2.
So the other property was?
Sir, K or A in this case into T of x. As in T of x1 plus x2 is equal to, T of x1 is equal to K into T of x.
This one is equal to what? Can you tell me? How can we
Sir,
write it?
alpha t,
Alpha?
alpha t,
Alpha 1?
alpha t brackets are x of 1
Alpha 1 T of x1
plus
plus
beta t, beta
alpha
plus
t
alpha 1 t x2.
This was a property. Basically, this is the property of linear transformation. This is how we prove that whether a given transformation is linear or not. Okay. And I told you that we can extend this property and obtain the principle of superposition. Look at that thing and tell me how can we write this thing by using principle of superposition or this property. This thing can be written as what? It can be written as x1 T of E1, okay, plus x2 T of E2, plus so on, plus xn T of En. We can write this if T is linear. This is what? This is principle of superposition. I told you in the previous lecture. So if this is so, further, can we write this thing in this form, T in the matrix form or in the vectors form, T of E1, T of E2, T of and so on, T of En. This is a vector times another vector which contains x1, x2, so on, xn. This is a vector product. If we multiply this vector with this vector, what do we obtain? We obtain this thing. Do you agree? So now, this is T of x. This is T of x. Okay, now this T of x is equal to A times x. Okay? This T of x is equal to A times x. It means this T of x is what? It is A times x. And here, what is this? This is x. What we can write here, we can write x, A times x is equal to T of E1, T of E2, so on, T of En times x. Now, if this x and this x is same, then what we can say here that A is what? It is T of E1, T of E2, so on, T of En. What is this? This is your standard matrix. Okay. What is this? This is your standard matrix of the given linear transformation P. This one. What we have to do in order to find the standard matrix of a linear transformation, we only have to find the images of unit vectors under the given linear transformation. What is this? This is the image of the first unit vector. Image T of E1 is basically the image of unit vector E1 under that transformation G, which is given. Okay. Now, let us try to find the standard matrix with the help of an example. In the previous lecture, we started with the transformation T from R2 to R3. And the definition of this transformation was, if I remember, please correct me if I write something wrong, it was 2x1 plus 3x2, x1 minus, it was 2x2 and minus x1 plus x2. Something like that. If it is different from that transformation, it doesn't matter. Just you have to see how do we write this standard matrix. Now this is the transformation, and we have to find the standard matrix for this given linear transformation. Now, what is this? This belongs to R2. Okay. This is your x, and it belongs to R2. Okay. Now, what are the standard bases of R2? These are 1, 0. Yes, and 0, 1. And this is what, in fact, it is E1, E2. These are the standard unit vectors. This is your E1 vector, and this is your E2. Now, under this transformation, we have to find the images of E1 and E2. Images of E1 and E2, how can we find? First we find T of E1, and what is this T of E1? It is in fact T of 1, 0. Okay. We just put this 1, 0 in this definition here. You get the T of E1. It is x1 is 1 and x2 is 0. So according to this definition, x1 is 1, 2 times 1 plus 3 times 0. Okay. Because here you have x1, x2. So next is 1 minus 2 times 0, and the next one is minus 1 plus 0. If you solve it, what do you get? 2, 1, minus 1. This is your T of E1. Okay, this is your T of E1. Now, you find T of E2, which is T of 0, 1. So now, x1 is 0, x2 is 1. You put it here, and you obtain x1 is 0, x2 is 1, you obtain 3 here, x1 is 0, x2 is 1, you get minus 2 here, x1 is 0, x2 is 1, you get 1, 0. So this is your T of E2. Now what is your standard matrix here? According to the definition, standard matrix is T of E1, T of E2. Okay. Now, if you put here T of E1 is a column vector. You put this whole column here. So it is 2, 1, minus 1. And what is your T of E2? T of E2 is this whole column. You put this column here, 3, minus 2, 1. So this is your standard matrix A. So corresponding to this transformation, the standard, if you want to write this transformation in the form of a matrix transformation, then it would be what? So this would be T of x is equal to A times x. And what is A? What is A? This is your A, 2, 3, 1 minus 2 minus 1, 1 times x. So this is how you can write this transformation in matrix form by finding the standard matrix of this linear transformation. I hope you get it. If you have any question, you can. No question? If you don't have any question, I'm going to give you an example, another example of this kind, and you have to write, you have to find standard matrix and you have to tell me. Now, let's consider this example, maybe this exercise. And T is defined from R4 to R2. Such that T of x1, x2, x3, x4 is equal to 7x1 plus 2x2 minus x3 plus x4, comma. Cheat. Comma x is x3, not 2. X3, R3. X2 plus x3, comma minus x1. So this is your linear transformation. Can you write a standard matrix and tell me what is the standard matrix? I'm giving you 1 minute. Okay, tell me the result. What is your standard matrix? It should be, let me write the answer. It should be 7, 2, negative 1, 1, 0, 1, 1, 0, and negative 1, 0, 0, 0.
Yes, sir, that's it.
That's it? Okay. You can directly write it from here as well. But just write in the coefficients of these unknowns. 7, 2, minus 1, and 1. यहाँ पे x1 का क्या है कोफिशिएंट 0, 0x1 और 0x4. यहाँ पे माइनस x1 है तो इसका कोफिशिएंट नेगेटिव x1 है, 0x2 plus 0x3 plus 0x4. So this is how you can simply write the standard matrix. But not in every situation you have this definition. If you are not given this definition, then how do you write the standard matrix? For example, I hope everyone has this answer. If you have any confusion, you can ask me. Otherwise, you can directly write it, but the formal procedure is to find the standard matrix is that one which I told you earlier. Okay? You write its standard basis vectors, so standard unit vectors, which is E1, which is 1, 0, 0, 0, because we have elements in R4, okay? Because this is an element in R4, so we have to write the standard unit vectors of R4. So it is 1, 0, 0, 0. In E3 is 0, 0, 1, 0. And E4 is 0, 0, 0, 1. And then you have to find their images, T of E1 and T of this, T of E2 and T of this, T of E3 and T of this, T of E4 and T of this. Okay. Now, what is this T of E1? It is T of 1, 0, 0, 0. What does it mean? You have to put x1 1 and all other zeros. X1, it is already 0, so you don't have anything here. And then 0, 0. Or similarly, you find all these images and put them in a matrix, in the column form. You get the standard matrix, as we did in the previous example. Now, if we are given this definition, we can directly write the standard matrix by looking at the coefficients of these components of this vector, image vector. But if we are not given this definition, how to write the standard matrix? Let me give you an example. For example, some basic linear transformations in R2. We start with R2 of the operators. T is a linear transformation from R2 to R2. Okay. First, we are going to discuss the transformations in R2 to R2. For example, 1. Write a linear transformation. Write a linear transformation that reflects every vector x in R2 about x-axis, for example. How can you write this transformation? Now, we have to look at R2. This is your R2. And for example, this is any vector in R2. This is in R2. Now, we look at the standard basic unit vectors here. This is, for example, this one is your E1, which is standard unit vector 1, 0. And this is your E2, which is the standard unit vector 0, 1. Now, if we reflect this thing about x-axis, this is your x-axis. ये आपका E1 unit vector है. We have to transform any element. We have to reflect element, these vectors in R2 about x-axis. Means we have to reflect it about x-axis. So this unit vector, when we take its reflection about x-axis, it will remain same. It doesn't change anything. But if we reflect this unit vector about x-axis, it will be what? It will come here, and it will become what? P of E1, it will become 0, minus 1. It was 0, 1. If we take its reflection about x-axis, it will become what? P of E2, sorry, not E2, P of E2, after reflection, it will become image. So T of E2 becomes 0, minus 1. Here, T of E1 will remain same after the reflection. Now, what will be the standard matrix here? P, this will be T of E1 and T of E2. What is the transformation here? Transformation is doing reflection of all elements in R2 about x-axis. Okay, what we do, in fact, we see how the unit vectors in R2, they will be reflected about x-axis. What will be the output when we reflect unit vectors in R2 about x-axis? So this is your E1. When we take its reflection about x-axis, it will not change. This is your second unit vector E2. If we take its reflection about x-axis, this is your x-axis. If you take its reflection, it will become here. It will come here, and it will become 0, minus 1. So this is what the transformation is doing. So we see the images of these unit vectors, and we put them here in the matrix A. The one is 1, 0, and the second one is 0, negative 1. Okay. This is your standard matrix. So the transformation will be defined by T of x is equal to A times x, where A is what? It is 1, 0, 0, negative 1 times x. Now this will be your linear transformation. Now whatever the vector you put here in this transformation, whatever the element here in R2 you put here in this transformation, it will reflect that point about x-axis. You can take an example, for example, maybe a vector element x, maybe 2, 3. After you apply this transformation on this 2, 3, what do you get? 2, 3. What do you get? 1, 2. And if you multiply this, what do you get? 2 minus 3. Now, what is this point? If 2, 3 is a point here somewhere, here 2, 3, then after applying t, this 2, 3 will go towards 2 minus 3. 2 minus 3 is somewhere here. Let me erase this thing so that I can clearly show you. So this is your R2, and you are taking some 2, 3 here, this point, 2, 3. After applying, this is your x vector. Okay? Now, what will be the T of x? T of x will be the same vector, but it will be reflected about x-axis, 2 minus negative 3. This is your x. So this is what this transformation is doing here. Basically, this transformation reflects every element in R2 about the x-axis. And what is its standard matrix? The standard matrix is this. Standard matrix will be fixed, and whenever you change the vector, this transformation will reflect that vector about the x-axis. I hope you get it. If you have any question, you can ask. Similarly, you can write a linear transformation which reflects a point in R2 about y-axis. Let me write a point. Let me write a linear transformation which reflects any point about the line y is equal to x. This is your now line y is equal to x. Now, if I take any point here or here somewhere, I want that transformation to transform this point about this line x-axis. So if this point is somewhere here, after the transformation, it should be reflected about this line, and it should come here somewhere. This one. I hope you get it. So I need to write a transformation which reflects this point, this vector x, about this line y is equal to x. It should come. So T of x should be this one. What this T of x will be, it will be, in short, it will be reflected about this line. So the position of x1, x2 will be changed. So it should be x2, x1. Okay? But I have to write that transformation. What will be the standard matrix in this case? Now you look at the unit vectors. This is your unit vector, this is your unit vector. This is 1, 0, and this one is 0, 1. Now, if you reflect this point about this line, x-axis, okay, this will go here and this will come here. So what change will be, will happen here after taking this reflection? Anyone? What will be T of E1 and T of E2 here? What will be T of E1 and what will be T of E2? Anyone? Can you tell me?
Sir, 0, 1 and 1, 0?
Yes, simply. This will become 0, 1 and this will become 1, 0. And this was basically what? 1, 0. This was what? T of 1, 0. When you take its reflection about this line, this will go there and it will become 0, 1. And this will come here and it will become 1, 0. And this is, in fact, 0, 1. So what will be the standard matrix in this case? The standard matrix in this case will be T of E1, which is 0, 1, and T of E2 is what? 1, 0. So this is your standard matrix which transform every vector in R2 about it. It will reflect every vector in R2 about this line y is equal to x. So you have to look at the unit vectors, where they are going after we apply the transformation. I hope you get it. If you have any question, you can ask.
Sir, I was wondering that what would happen if the point is at the third quadrant? Then it wouldn't really work because the standard matrix is all positive.
The reflection in maybe third quadrant here.
Yes, sir.
You tell me the point. Anyone? You tell me the point.
-3, -4.
This one is
-3, -4.
maybe somewhere here. -3, -4. When you apply this transformation, only the places of -3 and -4 will be changed. Any other thing will happen or not? आप ये ट्रांसफॉर्मेशन अप्लाई कर देना इस पे t of -3 -4 ये ट्रांसफॉर्मेशन क्या कर रही है? सिर्फ इनकी प्लेसेस को चेंज कर रही है. ठीक है? It will be multiplied with -3 -4. What are we doing basically? Here we have 3 -4, and after multiplying this matrix, what will you get? -4 -3. सिर्फ इनकी प्लेसेस चेंज हो जाएंगी.
Okay, got it. Thank you, sir.
But it will remain in the third quadrant. But ये यहाँ पे है तो यहाँ पे आता है. जब यहाँ पे है तो यहाँ पे चलेगा. So what will happen if the point is on the line? If the point is on the line, what will happen?
Sir, on the point पे y is equal to x है तो हम swap करेंगे तो फर्क नहीं पड़ेगा. X to x से swap करेंगे.
Okay, so this transformation will do nothing because it's on the line. Its reflection about that line is itself. I hope you get it. Any confusion?
हमारी लाइन ऑफ रिफ्लेक्शन कुछ और हो, जैसे x plus 2 है, y is equal to x plus 2 है, फिर हम कैसे करेंगे?
अगर y equal to x लाइन के अलावा कुछ हो तो फिर क्या होगा?
जैसे अगर वो ओरिजिन से क्रॉस नहीं कर रही.
Origin से क्रॉस नहीं कर रही. So this is your assignment. You have to write a linear transformation to find a reflection of any point about any line in R2. Okay, you have to write this standard matrix, and you have to show it in the next lecture or maybe somewhere during my office hours. This is your assignment. Okay, the procedure is same. Okay, you have to follow the same procedure. You have to look at the unit vectors, how they will be transformed after you apply that transformation. Now, let us define another transformation which rotates any vector about an angle theta. So this is your original vector, and you need to define a linear transformation which rotates this vector about an angle theta. And you obtain the new vector here, t of x. What will be your linear transformation here? Now, you know that here you have a unit vector here, this one, E1, it is 1, 0, and here, what do you have? E2, 0, 1. This is your 0, 1, E2. You don't have to look at these vectors. You have to look at the unit vectors, how they would rotate if we rotate that vector about an angle. So E1 पहले यहाँ है, इसको आपने angle theta पे rotate किया. The same vector. This is your theta. If you make a right angle triangle here, what will happen? If this length is 1, if you take this a right angle triangle, what will be this length? पास ये यूनिट लेंथ थी ना, आपने यूं ट्रांसफॉर्म कर दिया. ये 1 है, तो in terms of theta, what we can write here, it is basically आप अगर आप इसको दूसरे सेंस में लें, अगर आप इस यूनिट वेक्टर को रोटेट करेंगे तो आपके पास एक बेसिकली सर्कल बनना चाहिए ना, तो यूनिट वेक्टर विल कम हियर, यहाँ पे आता है, इसकी लेंथ इतनी है। अब आप यहाँ से इसकी एक राइट एंगल ट्रायंगल बनाएंगे, ये वाली, तो आपके पास या आप ये बना लें, ये वाली बना लें, ये लेंथ क्या होगी आपके पास, दिस विल बी योर कोसाइन ऑफ थीटा, और ये लेंथ क्या होगी, साइन ऑफ थीटा, ये होगी। And this point is basically what? This point is cos theta and sin theta. This point. Now, ये यूनिट वेक्टर जब ट्रांसफॉर्म रोटेट होगा तो यहाँ पे आएगा। अब यहाँ से अगर ये यूनिट वेक्टर रोटेट होगा एट एन एंगल थीटा, तो ये एंगल थीटा है। आप इसके साथ राइट एंगल ट्रायंगल नहीं बना सकते, यू हैव टू फाइंड दिस एंगल, दिस एंगल, ये एंगल कितना होगा, एनीवन?
90 minus theta.
Huh?
90 minus theta.
Yes, pi by 2 minus theta, pi by 2 minus theta. Now you make a triangle here with the angle pi by 2 minus theta. ये वाली बेस इसकी क्या होगी फिर, cosine of pi by 2 minus theta, और ये vertical height इसकी क्या होगी, sin of pi by 2 minus theta. तो ये point आपके पास क्या होगा, this point will be basically cosine of pi by 2 minus theta and sine of pi by 2 minus theta. ये वाला point क्या बन जाएगा, cos of pi by 2 minus theta. If we expand it, what do we get? Minus sine theta, and the other one becomes cosine of theta. So this is your E of E2, T of E2, and what is your T of E1? This is your T of E1. Which is cos theta sin theta. Now, what will be the standard matrix? It will be cosine theta, sin theta, and negative sin theta, cos theta. Okay, so the transformation will be what? A t times a times x, where a is defined here. Now, if you want to define, if you want to find a rotation of any point about an angle theta in R2, then this transformation will serve the purpose. Okay? This will transform any vector in R2 about an angle theta in R2. This will be your linear transformation. If you have any question, you can ask. So in fact, what you are doing here, you are basically rotating the unit vectors, not the original vector. Okay? What you are doing, in fact, you are rotating the unit vectors. This is your unit vector 1, 0. You are rotating here about an angle theta, and the other unit vector, which is here, 0, 1, you are rotating it at an angle theta here. And see what how these unit vectors will be converted into new vectors after we apply the transformation. अगर ये angle theta है और ये angle theta है, so this angle will be what? This angle will be pi by 2 minus theta. Okay, you have to remember this thing, because in R2 you can make right angle triangle either in this way or in this way. Okay, this one is theta and this one is pi by 2 minus theta. आपने दो राइट एंगल ट्रायंगल बनाई और कोऑर्डिनेट्स फाइंड करिए on that circle. This one. I hope you can.
Sir,
Yeah.
could you explain how we found E2 again?
Huh?
Could you explain how we found E2 again?
E2 में basically this unit vector, when you rotate it about an angle theta, it will come here somewhere. Okay? this unit vector. But you cannot find the coordinates of this point with respect to the y-axis. Okay? You have to find this angle, which is pi by 2 minus theta. Now you can find the coordinates of this axis with respect to x-axis. So that's why we are writing here pi by 2 minus theta. We are not going to use theta. Got it?
So we got minus sine theta exactly how?
This one is pi by 2 minus sine theta. अब इसके coordinates क्या होंगे? It will be cosine of pi by 2 minus theta, comma sine of pi by 2 minus theta. Okay. Cos of pi by 2 minus theta क्या होता है? If you expand it, you know cos of alpha plus beta. I hope. What is this? You know it?
I think I've forgotten.
Huh?
I've forgotten. I will have to revise it all.
Cos of A, cos of B minus sine of A, sine of B.
You can revise, you can remind that property and you can apply here. You'll definitely get minus sine theta cos theta. Okay? Because cos by pi 2 0 होता है, and this is in fact, let me tell you, this by time, it will be cos pi by 2 sine theta minus cos theta sine pi by 2. Okay? Cos pi by 2 is 0 and sine by 2 is 1. What do you get here?
Minus cos theta.
Minus cos theta. Cos होता है यहाँ पे. Cos होता है. Yes, और यहाँ पे sin होता है. So it will be minus sine. Okay, this is your identity. So you get here negative sign. Got it?
Yes, sir.
So this transformation will rotate any vector about an angle theta in R2. And there are many other this kind of transformations in my notes. You can see them. There are contractional mappings, contraction and expansion mappings. There are many other. I don't have much time to explain all of them here. Let me see them and tell you if there is some. Projection operators, you can just read them, projection operators. Or these are basically operators. Why? These are operators because any linear transformation from between the two same spaces is called a linear operator. I told you previously. So that's why they're calling it an operator, not a linear transformation. So the projection operator, you can see it. Orthogonal projections, you can see them. Rotational operator, I told you. Rotational, this was rotational operator, which we just defined here. Cos theta, sin theta. So, and a couple of more. Shear and dilation and contraction operators. Dilation and what is this basically? Dilation and contraction. Contraction operators. Dilation and compression operators is something like that. P of x equal to k times x. Means if you have any vector x here, then k times x will be what? K times x will be a bigger vector if k is greater than 1. If k is greater than 1, it means k times x will be a bigger vector. Okay? This will be your k times x. If k is between 0 and 1, between 0 and 1, if k is between 0 and 1, then this k times x will basically contract that x. It will shorten that x. So this will be your k times x if k is between 0 and 1, and this will expand or dilate this factor where k is basically greater than 1. If k is equal to 1, it will change nothing, obviously. So in that case, the standard matrix would be k0, 0, k times x1, x2 in R2. This will be your contraction or dilation operator depending on the value of k. So I hope you can do it. Next is expansion and compression. Expansion and compression is basically a special kind of this thing. If you put only k here, not here, okay? Not one, this one. If you put k only here, not here, then the expansion or the contraction, dilation or contraction will happen only on the x-axis, okay, not on y-axis. So in that case, what will happen geometrically, अगर आपके पास कोई वेक्टर है this one और आप ये x है x1 x2 and you apply this transformation k001. If k is greater than 1 or less than 1, for example, if k is less than 1, this vector will be contracted only towards x-axis. So this will come here, this one. But the y-axis will remain same. So this vector is now k times x1, x2. Because the height will remain same. This is your height x2. Okay, height x2 will remain same, but this was your x1. Now the new x1 is what? K times x1, where k is less than 1. Okay, so this vector will be contracted. अगर आप इसको एक स्केयर से डिनोट करें, ये वाला, तो new, after applying this transformation, the new scale will become this one. Similarly, अगर आप सिर्फ यहाँ पे 1 रखें और यहाँ पे k लगाएं, तो आपकी जो contraction और dilation होगी वो y axis के toward होगी, सिर्फ x axis fixed रहेगा. So this kind of contraction and compression and expansions are basically can also be defined with the help of these kind of linear transformations in R2. And there is another kind of operator which is called shear operator. Look at these operators as well. If you got any problem or confusion, you can ask me a question in the previous class. Okay. Shear operator. Shear operator are basically they are same kind of operators as these operators, compression and expansion. Now these were basically basic linear transformations in R2. Similarly, we can define same kind of transformations in R3, R3 to R3, but their standard matrix will be changed a little bit. Now we are going to see these linear operators in R3. For example, if you want to define a transformation which reflects any point about x-axis, now things have been changed. Okay, this is your x, this is your y, this is your z. Okay. If you have any vector here, x, now x has 3 components, x1, x2, x3. You have to find its reflection about now xy plane, yz plane, or zx plane. Now there are planes involved here. The reflection about xy plane will be what? Anyone, can you tell me? ये वेक्टर है अगर तो x ये है तो इसका रिफ्लेक्शन अबाउट x एक्सिस इट विल बी व्हाट? आपका जो x है वो रिफ्लेक्ट हो जाएगा -x में। तो आपका यहाँ पे t of x जो है वो क्या होगा? t of x it will be basically negative x1, x2, x3। ये होगा या नहीं? ये होगा ना? And your standard matrix would be what? T of x will be defined as A times x, and your A will be what? -1 xy plane। Remember, xy plane में क्या चीज नेगेटिव होनी चाहिए कि वो xy plane के को रिफ्लेक्ट करे। Am I writing correct? Anyone? XY plane का रिफ्लेक्शन लेना है एक पॉइंट का, तो क्या चीज होनी चाहिए यहाँ पे नेगेटिव?
सर y नेगेटिव होगा आई थिंक अगर x एक्सिस के अकॉर्डिंग हम ले रहे हैं।
XY प्लेन का रिफ्लेक्शन लेना है, XY प्लेन का। यहाँ पे Z नेगेटिव नहीं होना चाहिए। होना चाहिए या नहीं Z? देखिए XY प्लेन का रिफ्लेक्शन लेना है, X और Y तो सेम रहेंगे, रिफ्लेक्शन किस चीज का आएगा? सिर्फ Z एक्सिस का आएगा ना यार। ये वाली जो हाइट है Z वाली, ये x3 हाइट है, तो इसका रिफ्लेक्शन जाएगा नीचे यहाँ पे नेगेटिव x3 होगा। रिफ्लेक्शन अबाउट xy प्लेन है ना?
सर could you shade it? I can't imagine it.
बेसिकली ये xy प्लेन है। अगर मैं सीधा खड़ा हूं ना, ठीक है, मेरे नीचे पांव के नीचे xy प्लेन है और मेरी जो हाइट है वो z प्लेन है, मैंने अपना रिफ्लेक्शन लेना है, तो क्या चीज नेगेटिव होगी?
Z नेगेटिव होगा।
डेफिनेटली।
Yes, got it. Thank you.
So you will have 1 0 0 0 1 0 0 0 negative 1. So this will be the standard matrix which will give us the reflection about xy plane. क्योंकि इस वक्त मैं xy plane पे खड़ा हूं और मेरे पैरेलल हाइट में z plane है। अगर मैंने खुद को उल्टा करना है तो डेफिनेटली z एक्सिस जो है पॉजिटिव से नेगेटिव होगा ना। Anyone? Any confusion? Okay, I hope you get it. Similarly, you can write the reflection about YZ plane and XZ plane or any of them. This is how we define the reflection operators in our cube. Similarly, we can define projection operators. If I want to project this vector onto XY plane somewhere here, now this will be on the X and Y plane. Okay. So what component will become 0?
What were you asking, sir?
So this is your projection of this vector onto XY plane. This is your X, sorry, Y, this is your X. And this is your Z. So what would be the standard matrix if we want to define a projection of a vector onto XY plane? Projection means मैंने ये डस्टर है ना, ये 3 डायमेंशन में है, यहाँ पे इसका कोई X कंपोनेंट है, Y कंपोनेंट है, Z कंपोनेंट है, मैंने इसको XY प्लेन पे रखना है, तो क्या होगा?
Sir, Z is equal to 0.
Z 0 हो जाएगा। It means आपके पास जो मैट्रिक्स होगा, स्टैंडर्ड मैट्रिक्स, वो क्या होगा? 1 0 0 0 0। Okay, so this is your projection matrix onto XY plane. Projection on XY plane. Similarly, we can define projection on YZ and ZX planes, and correspondingly, we define here, right here, 0, 0, or 0, 1, 1, and 1, 0, 1, corresponding to the projection on YZ and ZX. These kind of transformations are defined in my notes. You can see them. The important one is, again, the rotational transformation in R cube. You have to take care while defining rotational operators in R cube. Okay. In that case, you have to remember that thumb rule in defining the cross product of two vectors. I hope you know what is the thumb rule while defining the cross product of two vectors. You might have studied this thing in your earlier classes of physics, maybe, or maths. Cross product of two vectors. So, usko zehn mein rakhiega. I hope you can write that rotational operator in R cube. For example, यहाँ पे अगर x है, यहाँ पे y है, यहाँ पे z है, and you have some vector, maybe this one, and you want its rotation, आप इसको थोड़ा सा about x-axis देखें. If you have this vector, and you want to rotate this vector about x-axis at an angle theta. So what will happen? You have to rotate it. This will be the rotation of this vector at an angle, maybe theta. You have to rotate it at an angle theta. You want to bring it here, maybe somewhere. So this angle is what? For example, this is theta. So now in this case, your x is fixed. You just imagine that if you have a 3D and you have any vector in that 3 dimension and you want to rotate that vector about x-axis. If you rotate, it will become a circle, which is a 2D shape, not a 3D. So it will become a 2-dimensional circle in which the x will be fixed. X distance fix होगा, सिर्फ change क्या होगा? Y and Z. Y और Z coordinate change होंगे, तो आपका जो standard matrix होगा, वो basically that will be 1, 0, 0, 0, 0. This is why, because x is fixed. सिर्फ change किसमें आएगी? Y और Z में. क्योंकि आपका ये x component है, यहाँ पे भी x है. ये y है, ये z है. अगर आप इसको देखें यहाँ पे x, ये y है, ये z. So x और x same रहेंगे. x में कोई change नहीं है. इसी तरह आपके y और z में चेंज आएगी. मींस आपकी ये जो 4 एंट्रीज हैं वो चेंज होंगी सर. पहली वाली रो और पहला कॉलम जो है वो सेम है. अगर आपने रोटेशन अबाउट x एक्सिस लेनी है, अगर आपने रोटेशन अबाउट y एक्सिस लेनी है किसी भी वेक्टर की, तो उसमें y की कॉरेस्पॉन्डिंग जो रो और कॉलम है वो फिक्स रहेगा. 0, 1, 0, 0, 0. सिर्फ x और z के कंपोनेंट्स चेंज होंगे. सिमिलरली z में आपके पास रोटेशन अबाउट z एक्सिस आपका यहाँ पे 1, 0, 0 और 1, 0, 0 यहाँ पे होगा. सिर्फ आपके x, y के कंपोनेंट्स चेंज होंगे रोटेशन. So now I hope you will understand how to define these rotational operators. These are defined already in my notes. You just have to look them. But take care of the rotation. Okay? If you are rotating about x-axis, any vector, then it will be a counterclockwise rotation, and the theta will remain theta. About x-axis rotation, it is counterclockwise. Counterclockwise rotation, theta will remain theta. But when you are doing rotation about y-axis in the same nature, in similar way, then this will become, I guess, clockwise rotation on 3D plane. And the theta will become negative theta. So keep this thing in your mind. You have to use that thumb rule while doing basically the rotation in defining the cross product of two vectors. So in that case, the matrix will be 1, 0, 0, 0, 0, cosine of theta, negative sine theta, and cosine theta. Because the rotation is only two-dimensional. Rotation is only in two-dimension. So it will be similar as the rotation in xy plane. Because in 3D, if you are defining a rotation over the x-axis, x will remain fixed. The rotation will happen only in y and z plane. But in second case, the rotation by using that thumb rule, that theta will become negative theta. Then in that case, you have to put here cos of negative theta, sine of negative theta, sine of negative theta, and cos of negative theta. In that case, you remember that cosine is an even function. So cosine of negative theta is cosine theta. But sine is an odd function. Sine of negative theta is negative sine theta. So you have to keep these things in mind while defining the other two rotational operators in R3. I hope you get it. If you have any question, you can ask. There's a question in the chat window. Let me see. What is it? Okay, that's great. The matrix was correct. Yes.
Sir, I have a question.
Gigi.
Sir, जब हमें R2 when we were doing it for 2 dimension, तो उस वक्त you didn't add stars. You मतलब normally we added 1, 0 because there were only 2 dimensions. So here in R3 you added stars because they could be any number. They could be 3, 4 depending on the rotation.
I have defined these stars over there. What will be these stars? This will be cos theta, minus sine theta, and cosine theta. Okay? The angle will come here in theta. If you want to rotate any vector about an angle, maybe 15 degree, then this theta will be 15. Cos of 15, sine of 15, and so on.
Okay, sir. ठीक है, got
Okay?
it.
The stars, basically, you have to write them. You have to fill them yourself. Okay? They will be either cos theta or sine theta, but you have to take care of the rotation.
तो सर हम cos theta ही मतलब जो depending on what theta is हम वैसे लिख देंगे कि हम उसको like we have to write the actual number.
Actual number, the actual rotation which you need. If I ask you to rotate this vector about y-axis or z-axis at an angle 30 degree, maybe, then you have to insert theta is equal to 30 degree.
Yes, sir, I understand.
Theta is basically a general angle which you can insert here in that matrix. You got it?
Yes, sir.
Okay, that's great. Then similarly, you can define dilations, compressions, and shear operators in R cube as well. So you have to define them accordingly. These are defined in my lecture notes as well as in books. Have a look at them. If you have any confusion, you can ask me in the next lecture. Okay? So you have to complete all these kind of operators in R2 and R3, which are given in my notes, maybe, as well as in books. You have to see them completely. Any question?
Sir,
I hope you understand. So today we are going to stop here. In the next lecture, we shall start composition of linear transformations. We'll see how can we compose two linear transformations to get a new linear transformation. We'll discuss this in the next one. If you have any question, You can ask me otherwise. Well, that's a good question. How did we determine whether the rotation is clockwise or counterclockwise? So you have to follow that thumb rule, which you have studied in physics. अब आपके पास अगर 3 डायमेंशन है, okay, तो यहाँ पे आपका x-axis है. Now, you put this thumb along x-axis. Now you see. Look, I don't know this one. This one. Is it? Okay. You have to use this thumb rule. Point the thumb along x-axis. And what kind of rotation is this? Is it counterclockwise or clockwise? You put your thumb, you point your thumb along x-axis and see this rotation. If this is counterclockwise or clockwise. And then when you point this thumb along y-axis, is this your counterclockwise or clockwise rotation? You have to look this. Now you put this your thumb pointing towards z-axis and see this is a counterclockwise or clockwise rotation. I think this is the rule. Hanzala, can you talk to me?
Yes, sir.
You have to use that thumb rule in order to find the rotation, whether it is clockwise or counterclockwise. If the rotation is clockwise, then your angle theta will be minus theta. Okay, because the rotation will be reversed. If your rotation is counterclockwise, then your theta will remain theta. You got it?
I think so.
So try it. If you don't get this point, we'll discuss this in the next lecture. Okay, everybody, think over it. How do we define the rotation, whether it is clockwise or anti-clockwise along x-axis or y-axis? Okay.
Sir, wouldn't it depend on the question? Like, sir, just आपने लिखा है कि rotation about the x-axis. So I assumed कि we would, in general, make it counterclockwise. And if it was asking about the y-axis, तो फिर हम उसको clockwise कर देंगे.
No. That rotation, I don't think so. Okay, rotation given होगी. Rotation हमेशा positive से negative x-axis की तरफ जाती है. अगर आपके पास यहाँ पे rotation about x-axis है, तो the rotation would be, I think, naturally it will be counterclockwise. If we are trying to find the rotation about y-axis, then naturally it would be clockwise. Try it and think about it. Okay. Again, when you point your thumb along y-axis, you look at your fingers, how they are rotating. How they are rotating. They are rotating clockwise. Clockwise. You put them yourself, draw a 3-dimensional axis, and point your thumb along y-axis. Your fingers are rotating how? Clockwise. If I look at my fingers, they are rotating clockwise. So this is the natural rotation of that vector. If they are those vectors are rotating clockwise, then theta will be equal to negative theta. Okay. Now, if you point your thumb here along z-axis, now the rotation is counterclockwise. Okay. Now your theta will remain theta. For example, in rotation, if you want to define a matrix which rotates any vector about y-axis, then it will be 0, 1, 0, cos of negative theta, and negative of sine of negative theta, and sine of negative theta, and cosine of negative theta. These expressions will remain same as in 2D, but only the angle will be changed. Now, using this definition of odd function and even function, cosine of minus theta is cosine theta, cosine theta. Now this will become positive and this will become negative, because this negative will come out and make it positive, and this negative will come out and make it negative. Okay? Got it? Any question? Maybe? Who was asking me this question? No question? Okay, I hope you get it. Let's stop today's lecture here.
सर वो नेक्स्ट क्विज में यही एपिसोड आ रहे हैं जो हमने अभी पढ़े हैं सारा.
हाँ जी, क्विज में यही चीजें आएंगी, लीनियर ट्रांसफॉर्मेशन, इनर प्रोडक्ट स्पेसेस, नॉर्म्स एंड समथिंग लाइक दिस.